Okay, so for today we're doing the solubility product. The syllabus outcome for today is derive equilibrium expressions for saturated solutions in terms of KSP, calculate the solubility of an ionic substance from its KSP value. So we're mainly just doing that first one today. So here's the answers to the revision questions. I hope you did them first. Ionic solids that dissolve by being solvated by water. The water molecules arrange themselves so that negative dipole moments are pointed towards the positive ions and vice versa. Insoluble salts generally release energy by solvation, less energy by solvation than it absorbs to break the ionic and hydrogen bonds. So the solubility product, what are we doing with this? Well, the dissolution of a solid salt into water is not a one-way reaction. It is technically an equilibrium reaction. As such, it will have a KEQ value associated with it. In this case, we call it KSP. So SP stands for solubility product. Now, it's called this because when we take our equation for the dissolution of a salt, so this one, for example, so AX BY as a solid is in equilibrium with X moles of A plus aqueous plus Y moles of B minus aqueous, or it could be a completely different number of charges or whatever. But let's just take this one as a super simple example. The KSP expression is given by this. So it's just um, the cation to the number of moles of cations, the anion times to the power of the number of moles of anions. Now, you might remember from earlier in the module, what do we do with solids in an equilibrium expression? We get rid of them. Okay, we treat them as if they're one because they don't actually vary in concentration, so it doesn't actually affect our KSP values. And so it's just a product. There's no dividing here. It's just that product. So two things multiplied together. The solubility product is calculated at the point where no more solid will dissolve. Now, if you remember what that's called, that's a saturated solution. Okay. This is because before this point, it is an equilibrium system. I've got here it's not an equilibrium system, but it is, but it's all the way to one side. Okay. But we need to reach that saturation point for it to be a proper equilibrium system. A solution where no more solid dissolves is called that saturated solution. And that's the point where our equilibrium comes to it. Now, the solubility product is therefore a measurement of how soluble a salt is. Okay, basically, the higher the KSP value, the more of our salt will dissolve. Smaller KSP value, the less of a salt will dissolve. The solubility product is calculated in much the same way as other KEQ values, and that's by using our concentrations. But solubility is often quoted in grams per 100 mils. And this is where people trip up a lot, is that conversion from grams per 100 mils to moles per liter. But we'll do some examples so hopefully you can understand what we're doing. So we need to change that first. So let's have a look at this one. A saturated solution of sodium chloride at 25 degrees Celsius has 35.7 grams of sodium chloride dissolved per 100 mils of solution. Calculate the KSP of the sodium chloride at 25 degrees Celsius. So what do we do? Well, firstly we need to convert the solubility from grams per 100 mils to moles per liter. How do we do that? We take our solubility in grams per 100 mils. Our moles per liter is per liter. So what we need to do is if there's 35.7 grams per 100 mils, then there's 10 times as much per liter. Okay. So if you can see where that's coming from, so we've just multiplied it by 10 basically. Now that's 357 grams per liter. 357 grams of sodium chloride is 6.1 moles. And so the solubility is 6.1 moles per liter. Okay. So we've got that 6.1 moles per liter. That's all fine and dandy. We now need to write our KSP equation for the reaction. Now, the reaction is always going to be the solid salt on the left, it's in equilibrium with our ions on the right. Okay, so if that's our reaction, our KSP equation is just that, concentration of sodium times the concentration of chloride. We then substitute in the correct values, so we got, I think, 6 point something. Before substituting the value we previously found, we also have to ensure that we are using the concentration of the ions, not the salt. So in this case, for our sodium chloride to sodium and chloride, it's 1 to 1 to 1. So we can just use those values. No hassle. Okay. So each of the values is going to be 6.1 moles per liter. So we put that in, 6.1 times 6.1, 37.21. So that's our KSP for sodium chloride. Let's do another example. So saturated solution of barium hydroxide at 25 degrees Celsius has 4.68 grams of barium hydroxide dissolved per 100 mils of solution. So we need to calculate the KSP of barium hydroxide at 25 degrees. So again, same deal. We need to convert solubility from grams per 100 mils to moles per liter. So we had 4.68 grams per 100 mils. There's 10 times the amount of that in a liter. We then change 1,000 mils to liters just to make it easier on ourselves. We then find out how many moles is in 46.8 grams of barium hydroxide. And we can say then solubility is 0.273 moles per liter. Okay. So once we've got that, we need to put into our KSP equation. So for that reaction, so barium hydroxide is in equilibrium with barium 2 plus and hydroxide minus, so 2 hydroxide minus. The KSP equation we get is that. So Ba2 plus times OH minus squared. Now, last question, I mentioned how we have to take into account the stoichiometric ratios, in that the value that we've just gotten is the solubility of the salt. Okay. Now, when the salt dissolves, it splits into its ions. Now, depending on the stoichiometric ratios, it could split into a different number of ions. So in this case, the salt and the ions are in a 1 to 1 to 2 molar ratio. So there's 1 barium hydroxide to 1 barium to 2 hydroxides. So we use the value of 0.273 moles per liter from barium, but we need to double that because there's twice as many hydroxides for the hydroxide ion. So it's actually 0.546. Okay. And so substituting those numbers in, 0.273 times 0.546 squared, we get 0.0814. Okay. So that stoichiometric ratio is very important for this, and especially when we go the other way, when we're given KSP and we need to calculate solubility. Super important there. Okay, so try it yourself. So saturated solution of copper 2 phosphate at 25 degrees Celsius has 6.35 micrograms of copper 2 phosphate dissolved per 100 mils of solution. So calculate the KSP of, that should be copper 2 phosphate at 25 degrees Celsius. Now remember, copper 2 means it's Cu2 plus, phosphate is PO4 3 minus, and that symbol after the 6.35 is micrograms, so micro is 10 to the negative 6. Okay, so pause the video, have a go at that, and we'll go on to the answer in a sec. Okay, answer. Oh, sorry, that's the KSP value that hopefully you got for that. Now, I don't think I've got the working out, but if you need it, come and see me. Now, summary, dissolution of an ionic salt is an equilibrium process at saturation. The solubility product is a measure of the maximum solubility of an ionic salt. Okay. And the hiccup is that solubility is commonly given as grams per 100 mils, but needs to be converted before it can be put into the KSP equation. Okay. That is all for today. Thank you.